in May next term. And so then on to today. It's a great pleasure to welcome Professor Kate Jones, who is at UCL, University College London, where she's Professor of Ecology and Biodiversity and Director of the People and Nature Lab, which we'll hear more about. And her research explores the interface between ecological systems and human health, with a particular focus on understanding how global land use and climate change influence biodiversity and the emergence of infectious diseases from animals. And she's pioneered a lot of innovative methods that combine AI, citizen science, and ecological monitoring to track ecosystem and wildlife health and its implications for human health. So lots of things you span there with lots of enthusiasm. So over to you, Kate.
Thank you. Oh, hi, everyone. Come in. Just give people a few minutes.
Give them a second, yeah.
Well, it's absolutely fantastic to be here and really excited to talk to you about some of the work I've been doing. So when I was trying to put this talk together, I was thinking, it kind of gave me a good chance to reflect on the things I've been doing in this space of AI for nature recovery. And I've kind of tried to give you a journey through, my journey through, and where I kind of really think this field is going and what maybe we should be doing next. And then I thought it was a bit mad. So I don't know, but I'm here now, so let's go with it. So see how it goes. So as Linda said, I'm Kate Jones. I'm originally a zoologist, and I kind of got into mathematical statistical analyses of large data sets pretty early on, and that kind of built my experience with understanding how you use data to make to inform ecology and evolution, but also and more latterly in my role as director of People and Nature Lab, how do you use this knowledge to make better solutions, to make better decisions about how to manage our environment and our planet. So the talk really is in 3 parts. Oh, hold on, I just wanted to tell you about that image. So this is an image from Stroud, where I sometimes live. And this is in the town centre, and this is a fantastic street artist called ATM. And they generated this whole street art on the curlew. And Stroud is so right on that they were saying, well, what about all the ecology and the soil and all of the networks and the ecosystems? So he came back and painted the soil back on. So this is just to give you a kind of understanding of this kind of whole pattern of ecosystems and how to manage them better is what we're trying to do here, trying to do in your centre and trying to do more globally and to try to understand how we go from the data to decisions. Okay, so 3 parts then in this trot through. Why is nature recovery important? I've only spent a few minutes on that because I'm hoping that you all agree that recovering nature is important. I'm gonna go through some of the technological advances and also then talk a bit about my journey through data to decisions. And you can see where I've ended up and where I think the next steps are. Okay. Okay, right. So in the time I've been working on this, so I got my PhD in 1998. Amazing. It's like replies to scene. I've really seen the massive shift in our understanding of the criticality of nature. And I don't just mean us in this room, because we're all kind of bought into that idea, hopefully. I mean, the people that come to Davos every year and make these big global decisions, and that's this slide here is the kind of the World Economic Forum's assessment of the risks to the globe and to our society and economy in the next 2 or 10 years. And that's not just us, that's these global world leaders that fly in on their private jets to Davos to make these decisions. So in the 10 years, you've got 6 of the biggest drivers are all environmental, biggest risks are all environmental ones. And this is for 22, 23, but very similar thing. They do it every year. It's a very similar picture for this year as well. So there's been this massive shift. And I don't think you have to take a step back to realize where we were in 1988, 90s, and how central this problem is becoming to global decision makers. And I think it's really important to realize that change has happened. And also there's a massively growing evidence base about how important intact ecosystems are to our health and well-being. And this is a paper by some of my students and postdocs. Rory Gibb led this. We were looking at how ecosystems are changing over the world using the PREDICT data set by Tim Newbold and Andy Purvis. And we were looking at either a managed or an unmanaged site, or wild or rewilded site or whatever, and then looking at the difference between those different species present. And then, so that's the PREDICT program. But then we looked at whether the species which were in the more damaged or managed systems were more likely to give us an infectious disease. And that is true in generally across the planet. So this is 6,000 studies across the world. And millions of data points. In general, we're creating these really sick environments where we're much more likely to have species present, which will, give us an infectious disease or a spillover event. So the evidence base is growing. I just use that as an example, but also in a more hopeful way, our kind of understanding of how we solve these problems is also really changing too, like having a much more interdisciplinary approach to problem solving. And I put up the nature-based solutions because nature-based solutions is based at Oxford. And I think that's a really great example of pulling all these different aspects together to solve these big problems. Okay, so there's this recognition of the nature is a critical component of our planet, and that's reflected in our policy context. So we have our Montreal Global Biodiversity Framework, which is supposed to be a global agreement, which has been signed by many countries, not all, and has been ratified by some. So for those in the audience that don't know what that means that there is no international law. Countries can agree to sign something at an international conference, and then the only way it's actually enacted in reality is by a national law being passed in that country to carry it off. And that's what's happened here. UK has agreed to meet these targets and has ratified them in some of these laws that they've passed. So I mention them because they have important guidelines and targets that we have signed up to and are agreed in law. So if you haven't dig in to the terrible wording of this of this framework, so please don't read this. I'm just illustrating it. But we've signed up to kind of monitor, populations of species, looking at the trends, having net positive biodiversity by 2030 and a restoration by 2050. Okay, that's a really big deal. It's a really big deal as we're kind of declining like this. So there are huge amounts of data that are required to see whether we've even met these targets, let alone the action that we need to restore these habitats. So there is a really massive need for data to inform these targets. And I feel that we're nowhere near where we should be in trying to get those data. Now, I work a lot with engineers and computer scientists, etc. And they pointed me towards this kind of schematic about like the history of human activity over the last few hundred years, where we kind of started off at industry 1.0 and maybe we're industry AI now, I don't know, but industry 4.0. And that kind of journey between 1 to 4 has been really interesting because it started off with the kind of mechanization, steam, like the Satanic mills of the north. And then we've got like big car factories, industry 2.0, where we've got assembly line, electrical energy. And then industry 3.0 would be, say, a modern car factory where we've got automation, computers and electronics. And now we're moving into these cyber physical systems, say like an Amazon warehouse, which is sensing the environment and then taking decisions about that environment and then changing those actions. So having these Internet of Things and these networks in order to kind of manage our productivity. So, you know, where do I think biodiversity monitoring is and generating this data? I think we're here. We're here, and we probably need to be over here. So we need to really scale up what we're doing at not just the amount of biodiversity, but the areas that we're monitoring in order to meet some of these targets that we've set. Okay, so how are we doing? So in the last decade, we've seen an extraordinary revolution in the number of sensors and AI tools and analysis tools that are around to help us to do this. And I'm going to go through some of these in very, very quickly and point out some examples from my own work. This doesn't like me. Okay, so this is a figure from a really good review, if you're interested in this, in Frontiers in Ecology and Evolution, just kind of showing the kind of technological advances which have happened in the last few years. And these kinds of new sensors like acoustic, eDNA, LiDAR, all these kinds of activities help us understand something about the nature in front of us of biodiversity. So it could be about the traits, it could be about the abundances, but it also could be about where things are, the distributions, and also the interactions, really importantly, the interactions between species. So these new technologies help us do that. And one of the oldest ones that we've had is us and the observations that we have been making about the environment. And that's really scaled up in the last few years in generating huge amounts of data from platforms like iNaturalist and many others that are generating these kinds of observational data, which are really, really valuable. And I put up this slide because it really shows the power of those networks. And this is the State of Nature report, which is published every couple of years, which is organised by RSPB, Royal Society for Protection of Birds. And they generate they put all of the data together from all of the citizen science community projects, NGOs across the country that have been spotting wildlife and putting it all together to tell the government what the state of the nature is. And that's incredibly powerful. And these kinds of reports are powerful flags to decision makers that there's something that they have to do. And there's also powerful flags to the rest of the country that our country is in a dire state. So we're trying to, these are very good at raising awareness and also changing minds. So those data have been used to set some of those targets that we have in the different policies that we have been making. Okay, so not just citizen science then, but there's loads of other things going on. So you can see the hockey stick curves of these words, like advances in computing, advances in genetics, and eDNA, for example, citizen science, eBird, iNaturalist, Bayesian models, occupancy models, all of these things are kind of massively increasing as we've gone on for the last few years. So AI is a really big accelerator of this. And so that we're all on the same page in this room, I want to just describe what I think AI is so that we are all understand these words which get bandied about in the media. So AI really is just an algorithm which is capable of achieving similar to human performance on different tasks. So AI, like, so this is a very general term. It's so general that it often means nothing. Right? So when people say AI, that they probably mean something else. But this is what AI is in the kind of mathematical definition. And then machine learning is a sub part of AI, which is generating a function. So understanding how one thing is related to another. Does that remind you of anything? That's a regression. I mean, it's a regression. So you can do them in different ways, like with images or with sounds or with text, but it's just a regression. So this is a lot of hype for something that you already use probably every day, or maybe not every day, but that you know of and you know well. And then deep learning is, please don't quote me. Deep learning is just a different way of finding those relationships between variables. So it's a different way of searching. Many, they call them layers. They're just ways of figuring out the relationships between different variables. But it's a regression. So don't forget that when people are blindsiding you with that. Okay. So I'm going to talk about three different types of machine learning in this talk. I'm going to talk about something called supervised learning. So that's when you've got a bunch of labels, like this is this call, and oh, this is this, oh, these faces in this room, and I've put a label on everybody's face, and then somebody gives me a face at random and I can tell them what face it is or who it is. That you've labeled those things and they're called supervised learning. Unsupervised learning is when I've got a bunch of faces and I'm maybe clumping them into different colors of the coats or different eye color or whatever. That's, remind you of anything, that's a principal components analysis. So again, these are just words which have been kind of co-opted that we already know. Reinforcement learning is more agentic. So you're trying to optimize something. So say that you're trying to optimize the design of a nature reserve and you give an agent the rules that you want to optimize on, and it will go out and find how to do that. So that's just an agentic kind of reinforcement learning. There are many others as well, and they're changing every day. So this is probably old-fashioned now, but Simon Prince is fantastic, and he's got a whole book on this. So if you want to learn more about this, then it's really good, really, really good book. Okay, so let's talk about one of the first sensors, which are really, really important and a really amazing tool, and they've really developed over the last few years, and that's camera traps. So this is collecting visual information around in the environment, and they've been used for many years, 100 years or so, typically for hunters to figure out where their prey was, the human hunters to figure it out. But also they're incredibly powerful storytellers. So these images that they create are really fantastic in communicating a story. So this is a story of from ZSL, so my friend Chris Carbone. So he's got a network of camera traps in London, and they found a pine marten for the first time, and it made the headlines. So these are really powerful things, and powerful stories, and also powerful ways of understanding what's happening in your environment. And this tiger, oh sorry, come back, tiger. This is a study that I have done in Nepal across oh, I don't know where he's gone. Come back. So you missed him. So this is a study that I've done across Nepal, looking across a nature reserve to an outside area. Oh, amazing. Thank you. So we've put camera traps across this gradient of anthropogenic pressure, and you can capture some amazing footage from the animals there. And I know that you're all looking at him because it's amazing. It's an amazing image. So these are really great tools. However, they're a total nightmare to analyze, right? So you've got millions of images, or what can you actually do with it? So advances in AI have meant that you can actually unpick some of these patterns. So firstly, detection. So where is it in the image? What species is it? So that's also possible. Individual classification. These are my kittens, Hattie and Bear. And then interactions between different species and the environment, but also habitat assessment as well. This is coral reef analysis, looking at how damaged each coral was. So those are all possible using these kind of new supervised learning techniques that I just told you about. Okay, so there are a number of tools, and literally I put this slide together last month, and it's changed already. So these are rapidly improving all the time. So you've got mega detector, which is a really interesting general model, which can tell you whether it's an animal in the recording, in the image, a vehicle, or a human. And now there's one that does more species as well, but it's not complete coverage. And then you've got platforms where you can upload images to ID things. Again, these aren't perfect, and you actually have to pay for this one. But you know, there are these amazing tools. And then there's WildMe, which is looking for individual recognition of different individuals within submitted images. So these are fantastic new developments in trying to process all of these amazing images you might have collected around your site when you're trying to do the monitoring. But there are some issues with these. The main one is the domain gap. So most supervised models rely on you labeling whatever it is in the image and then creating a model, regression model, to then figure out what the species is that you have in unlabeled images. And you have a domain problem because most of the labels that we have are of pictures taken with a camera on Safari or whatever of that image, rather than a random kind of scrap picture of an animal's leg or part of a leg. So you've got a massive domain shift issue. So some of the models trained on those images are very difficult to apply to a camera trap set of images. And also, if you think about it, you have millions of images maybe, but from say 10 sites. So you've got a really limited background of the images. So when you try to generalize that model to another area, it may not work very well at all. So they're very brittle, these models at the moment. So it's very difficult to use them and generalize them. And then, of course, if you're really interested in a really rare species, because that's why you put the cameras out, you're only going to find them occasionally. And so you don't have enough training data for a good, recognizer, a good classification accuracy. So there are some really big problems with this domain. And I think actually this is interesting to the computer scientists because these are unsolved problems which need to be kind of fixed with the domain data that we have. But yeah, very exciting. So it's not just camera traps of tigers in the pool. You can use it on pollinators. So this is a pollinator study that's been looking at, it's monitoring a whole area to see what kind of species they have. And then this one is a really interesting study that started off in the Netherlands, but CEH have also adopted it. It's called the Amy trap. So it has a moth classifier in it. So it has a light, the moths come to the light, and then there's a video that takes the videos and then can ID the species to a certain extent. So these are incredibly powerful tools that we can use to start to analyze the data that we have. So that's kind of images. And I just wanted to talk a bit more about acoustics, because that's where I started this journey, thinking about creating these big data sets was with acoustics. Now, you can use the same models that you use for the images for acoustics, and that's what we do. So we turn the acoustics into a spectrogram that you can then see, and then the models use vision models to analyze sound. So it's the same kind of process and the same problems apply, but they have some specific issues. So we went through some of these problems in a fantastic series for WWF by Ella over there. So we kind of tried to survey what the issues were and how to do this kind of stuff. And, it gave us a bit of space to think about the problems. So the sensors have really come down in price. So this is just a graph to show the price up on the left and the type of sensor, whether it's a sensor only, just listens, or it records, or it's a self-contained unit. And the blue is aquatic and the green is terrestrial. So you can see that they've really dropped in price and increasing in sophistication. And the main reason really is the development of audio moss, which is is Alex Rogers, who's in the computer science department here. When I met Alex, he was in Southampton, and I helped him develop the audio moth to do ultrasonic frequencies, a wider range of acoustics. So these are very cheap little sensors you can put out and leave out. And looking at the data that you can get from these, they are very similar to, well, not the same, but you know, they do a reasonable job approximating some of the recordings comparator to a really expensive version of a hydrophone here. And this is done by my student, Ben Williams. Ben has been actually piloting and making sure that you can use the audio moth underwater as well. So he calls them a hydromoth. Anyway, so the sophistication of these vision models for sound has massively increased over the last few years. And this is a kind of summary of some of the things which are available. This is from a site called Backpipe, from one of the students on an EU grant that I'm on. So he just was trying to summarize all the types of models there are. And you might have heard some of these, like BirdNet. Merlin is on your phone, so you can use that on your phone. There's something called Perch, which Google has developed. And we have one called Bat Detect, which is obviously the best one. This was done by a bunch of us in the lab, but mostly Ocean, who's now a computer science associate professor at Edinburgh, and Santi, who's a lecturer at UCL now. So we have a BAT model, which uses these vision approaches, but also does quite a few clever things that these don't. So firstly, it finds calls in the recordings, which many of these don't. And then it gives you a cleaner kind of image of the recording. So then you can use it to do other things with it. And this Backpipe GitHub page just uses those models to try to figure out from a set of known calls, known birds actually, which ones would help you distinguish those different calls. So it just is a little comparator website. It's really good. So have a look at that. Okay, so not only the AIs have been amazing, but the tech that you can use to get the data. So this is Sarab Sethi, who's a student on a project on the Biohealth project, this WWF thing in Nepal that I showed you, and also as part of the SAFE project with Rob Ewers at Imperial. So he developed this platform where you could have a sensor, Raspberry Pi, attached to a microphone, and you would leave it out in remote location, powered by solar energy, and then it would send all the data to the cloud. So this is really revolutionary at the time in thinking about how you would gather loads of data, and then instead of going into the field, you would have it on your server at home. Well, who's got a home server? Well, maybe some of you, but maybe the university one. So then you can use things like the BirdNet to process all that data and then have that kind of whole system. So he's done a little startup on these bug devices to kind of operationalize those, commercialize those. And he's been developing it across Norway to get the Sounds of Norway project up and running. So these are really kind of powerful things. The next kind of thing, next iteration of this is actually not sending the data to a server, but actually processing the data on the sensor. So this is called Edge AI. And this is something we started in 2016 with Sarah Gallagher and Ella and a bunch of other people from UCL in our new campus in the Olympic Park. So we put a bunch of these sensors up around the Olympic Park for bats. And this is a kind of having a nightly live feed of the bats which are detected on the sensor and then sent to a server. So you can see it in real time. It means that you don't have those kind of upload issues. You can process the information on the sensor. So that was fantastic. We did those on a really old Edison board. Nobody even remembers what they are. They were like at least 5 years ago. Oh my God. So they're gone now. So we're trying to think about what's next. And so a couple of my students, so Santi and Ord, were trying to think about how you would do this for the future, and decided that the hardware was moving so fast, we'll do some software. So they created a kind of software patch in Python, which means that you can kind of use any device that's capable of processing information and then communicate that up to the cloud with your device, with your classifications. So this is called Occupy, which basically collects all the data up, does the processing, and sends the results up to you. So it means that sorry, keep pressing that. It means that you cut down on the information that you're transmitting. But of course, the downside is that you're reliant on the AI classifier to perform the classifications accurately, so you don't keep the original data, which can be a problem. Okay, and this is it in use. I'll talk about that project in a second, but it's just a Raspberry Pi plugged into a microphone, put into a box, and then plugged in and then left. Okay, so great. This is all great. I've got too excited. There's loads of new data, there's loads of new sensors, loads of new tools. But actually, what is it all for? Like, we have all this data, great, but like, what can we do with it? So this is kind of the last part of my talk is really going from, okay, we can do this, to what does it mean? Okay, so when you think about the processing pipeline, many people stop here. So it's just about acquiring the data and processing it. And that's where a lot of people just stop. But actually, there's a huge part of that is about what you're trying to do at the end with the data and how are you processing it. And there's a huge pipeline that you have to think about when you're starting to collect data like this. And also, and the most important thing, what on earth are you trying to do with it anyway? Like, what's the question that you're trying to achieve with the data that you've collected? And so I've done it myself, collected huge amounts of data, absolutely no idea what my theory of change was, or how you're measuring the actual impact and the outcomes rather than the outputs or the inputs. So I think it's really important to have that when you're starting to collect these massive data sets. So where is it we want to get to? I think it's really important to think about. We want to understand how environmental change and anthropogenic pressures are changing communities of populations and their networks, because that relates to function. That's what we're trying to get to, because we want to reverse it. That was what the 2030 and the 2050 targets want. So, okay, let's start from there and then let's work backwards. So species react differently to change. And so we need to somehow pick that up in our monitoring. And we could do that with behavior, occupancy abundance, community occupancy, species richness, something. We need to understand how these curves are happening so we can see where the tipping points are, for example, or understand how to intervene to restore nature. And I guess when you think about acoustics, it's got some really big problems that you really have to think about when you start to pull this inference pipeline together. Firstly, that if you're using an AI, you've only got a modeled ID. So it's not real, it's a modeled ID. So there are lots of false positives and false negatives in those data that you need to think about when you're putting them into a model. Often, as I talked to about the curlew, that's a rare species, it's not often heard. It won't be in some of these training data and you won't pick it up. Oh, hello. And there's also this domain shift that I talked about with the cameras. That's also true in recordings. If you're recording in a new place, you might have different subspecies that are calling differently, or cryptic species that you thought was the same species, but actually is different. And then if you're trying to work out abundance, then calls don't equal the number of individuals. So you have to really think about what you're going to do to that. How are you going to deal with that? You could try to standardize it over time, or try some new statistical models to try to account for that as you're trying to do inference on your data. Okay, and then finally, calls are really hard, right? They depend on the weather, the structure of the habitat, but also the directionality of the call. And when you think about bats, they echolocate at high frequencies. High frequencies attenuate in air really quickly. So you have to really account for all of these things when you're dealing with these kinds of data. Okay, so I'm going to take you through um, a little summary of how I've got to where I'm going to describe to you at the end. And these are through a series of projects. So let's go. So this was in about 2006. I decided that I was going to drive around most of Europe collecting data on bats for a landscape level project on how the landscape was changing. I had literally no idea how I was going to analyze any of the data. And I collected 2 terabytes, which I thought was like enough to power the moon. I thought that was the biggest thing I've ever seen. But now 2 terabytes is not, I probably store that on the little pen drive you gave me. I thought that was amazing. I didn't know how on earth I was going to do it. And I did most of it by hand. Right. So I've still got post-traumatic stress disorder. So I created a key with some colleagues that we looked at the call shape and the peak frequency, and I measured the calls on the computer. This was like 2006, 7, whatever. So I thought there must be a better way, right? There must be a better way. So we developed new tools. So this was a hand thing tool. And then this project, I was really interested in this landscape. Hang on, let's go back. I went through Ukraine and Russia, Hungary, all those places that you wouldn't be able to do now, Bulgaria. It was an amazing project, but it really taught me about having an analysis plan maybe at the beginning. This project was with Alex Rogers and Diego Ferreira, who was a student at the time. And we were trying out the audio moth for the first time with bats, and he was from Madeira. So we were like, let's do Madeira. So they've only got 3 bats in Madeira. So we did the whole of Madeira. So we did a stratified random sample, sent him off on a motorbike. That was the year there was mass fire across Madeira. So he was not very safe for a large part of this. So that was unfortunate, awful. Sorry, not. But that kind of taught us about how successful these could be. We put them in little plastic bags because there weren't any cases at the time. And Ricardo came on board later just to help out with the analyses and get it over the line. But, we managed to kind of understand the distribution of those species, very rare species in Madeira, and then their correlations with their different habitats. And then this one is part of this series of driving around all of Europe. We set a whole monitoring program up for 10 years in Jersey, just temporarily forgotten where Jersey is. It's just off the coast of France. So they surveyed Jersey for 10 years by driving around in these transects and strapping a microphone to the car. And we've been generating these kind of trends of the different bat species across that time period. So this was with an ANN artificial neural network that we developed in 2012. So gosh, that was a nightmare, but we actually developed an algorithm that semi-worked. And then we applied that to all of the UK. So this is a study with the Bat Conservation Trust with Ella and a number of different students and projects using the audio moth, but then developing this pipeline with our new algorithms, Bat Detect and Bat Detect 2, to classify these recordings, so collected by citizen scientists and then processed. And then finally, we the park data, we analysed the park data using Bat Detect to figure out, what's going on in the park. These are constant data, day and night, for 6 years. So you can pick up the events at the stadium, the Olympic stadium. So every time there's an Olympic stadium event, all the bats and probably all the birds disappear. And that effect is probably, I don't know about this, Ella. You need to look at that again. That lag. I don't know. You need to look at that. So that possibly it's still happening a day after the event as well. So these are serious things. So it helps us design new landscapes and new city into how people and nature are interacting in cities. And then this one is really new. We have done a partnership with Yeo Valley Farms. They've got a big dairy farm, a kind of show farm in Somerset in Blagdon. And this is the north part of their farm. And we've put occupiers out across that farm, and they generate data in situ all the time. So this was from last night when I downloaded the data. It's just on a website, so you can have a look at it. So this is last night, and it gives you a BirdNet algorithm, and it's just processing this data and telling you what species there are. So of course, there's no filters on these. Well, there's a bit of one that Ord put on that said other, which is the ones which you don't think are right. But you know, those need more processing. But that's a really interesting way of understanding how they're managing their site, and they're really interested in this wood pasture. So they're trying to convert their pasture into woodland, but also keep the grazing. So we were just looking at how successful that might be. And then this is camera trap one that we've been looking at across the Masai Mara. I talked earlier today to Yadvinder's team. I'm just looking at the time. What time is it? Okay, yeah, fine. So we put all these camera traps out across a gradient of human pressure. So these are camera trap dots where we put the sites up. And there is a gradient from protected areas, completely protected areas like here in Mara Triangle. And then you've got Mara North and a number of other conservancies, which are mixed use spaces with the community. So they graze cattle, but also they get money from tourists coming to look at the wildlife. So we were interested in, you know, how does grazing pressure and human settlement proximity, you know, affect the number of species that are there, and how does that work? So this is, I mean, just dwell for a second on this. This is 8.5 million images. We developed our own AI. It took 6 years, and there's one slide from that. So it's great. But it's really interesting. So there's a nonlinear response to cattle pressure from mammal community occupancy. So at a certain point, mammal community occupancy increases with cattle pressure and then declines. And then with sheep and goats are just horrendously awful wherever pressure you put on, and the community just declines. So they can't coexist with them. And humans, to some extent they can, but at a certain point they just can't deal with us being close. So, you know, this community occupancy is hiding these responses. So there are different responses for different species. And I show this because we need to start understanding how species are responding to pressures and try to maximize our interventions to help them coexist with us. So just finally then, the same kind of idea for acoustics in Kenya did not work at all. And that's because we don't have the libraries in Kenya that we need to process these information. So what we ended up doing was using some of these embeddings that I talked to you about before, and these big models to cluster similar calls together and then cluster them into functional groups. So then we could analyze them in functional groups. So that's something that's ongoing, but that is a problem with some of the acoustics in areas which we don't understand. And this is another approach we use at Coral Reef, where we had a Google, we worked with Google to have a little platform where you could give it a few of the recordings that you wanted, say, on snapping shrimp in coral, and then it would train itself using one of these foundational models. So this was a kind of few-shot learning model, which was really interesting, enabling Ben to have a look at how coral reefs were recovering and which species were present or not. Okay, so AI has been a massive game changer in this acquisition and processing. But, you know, what's the next step? Can we think about how we do model inference better with AI? and I use AI in the most general sense there. And also this one, how do we use that to then make better decisions? So one project that we've been thinking about and published recently is using multimodal learning. So we have text and images together, and so text and image machine learning models together, so that you don't have to program and train these data sets. The kind of pair matching has already done that for you. So if you've got a camera trap set, for example, and you want to know something else about it, like how many have got collars on, it would go and find those for you in those sets. So these are really kind of cutting edge tools in this multimodal approach, which is really interesting. And also, this isn't one of mine, this is one I just saw, using these language models to extract data, to then process that information, and then build decision making off that. And this is looking at the conservation evidence database and using a language model to pull out some of those big trends. Okay, so I talked to you, I'm too excited, and I talked to you about all these projects I've got, all this data, but I just want to end on just a thought, like, what does it all mean? I don't think we're doing this in the right way. I don't think having loads of data is going to help us restore nature. And so what I think we need to do is start off by pulling all the data we have and maybe trying to build more mechanistic understanding of how these work. And I think these data networks can actually help us, because we can pull the information from them to parameterize or understand those networks. And AI has a massive role there, because AI could help us scrape this data, pull the data together to understand these patterns. And then things like mechanistic approaches, where you're defining the relationships between things, are really interesting. And we should be starting to build these ecosystem-based models to help us process and understand the implications of management decisions. So I just want to end with this paper. The Mattingly model has been around for ages, but it's a kind of mechanistic model that tries to recreate ecological processes. So we need to look at that again and see how we can put kind of human dimension into there, to then see how we can start to understand those processes and how they're reacting to human interventions, to start to build these stories around how we can restore nature most effectively. And this at the moment does not have any human activity in it, so it needs to be coupled. And we can use the existing biodiversity data to parameterize it. And then another kind of aspect of the AI models I've seen recently are these physics-informed models, where you have maybe a mechanistic model, and then you can use the AI to learn some of the physics to then shortcut some of the processes. And this paper came out in 24, which is about the global circulation model and a climate model. And they use a bit of, I think it's a graph neural network, to actually help them understand some of the physics, to then shortcut the processes, and they can speed up the entire model, so it works like 10 times quicker or something. So I think there are huge opportunities here. Of course, I haven't talked at all about ethics, and I think we have to be really mindful about using it in a really acceptable way and a very careful way. But I can tell you that the things I can do now, I can never, ever have dreamed of being able to do a few years ago. And now we need to sit back and think about, what do we do next, and how do we make those decisions to restore nature? So thanks. I'm just going to finish then on some summary. Nature recovery targets depend on us having robust biodiversity management, which we don't have. These new technologies are amazing, but there are ethical considerations, and they're not good at decision making yet. We need to be very careful what we collect and why. AI has been great at the start of that process, but let's have a think about how it can help us next. And then I think the future of nature recovery requires predictive models and stories to tell people, like, you do this, this is what's going to happen. with some error margin. So thanks very much.
Thank you. Nice overview. So let's open up to questions. Anybody want to kick off? Take one here.
Hi, thank you. That was really interesting, and especially sort of the things you were beginning to touch on at the end. I found really interesting. I was wondering, sort of how you thought the current, I guess, AI hype plays in with this, because obviously, for most of the talk, you were talking about models which aren't LLMs, which are currently sort of where all the attention is being driven. And I was wondering if you think all the attention around that is helping the development of these technologies, or whether actually sort of the focus on this sort of general AI that can do everything is actually hindering cases where cases like this, where sort of more specific purpose-based models are more helpful.
It's a really interesting question, very complicated, because the effort that's gone into developing these language models does help with creating these specific models, because the researchers are learning more about how these systems work. And a language model is just the same as a vision model, it's just with text, right? And then so some of the same methods are helping this as well as language models. I do think it's really hard to get AI people to actually be interested in biodiversity and climate change when they can make 150,000 off when you graduate, right? So at these AI in these companies. So it's really hard to get people to want to work on these problems. And the way that I've tried to do it is that they're interesting computer science problems as well as being interesting ecological problems. So does it not help? I don't know. I mean, there's a lot of energy in the field. I think there's a bit of a clash of culture. I think the computer science conferences publish tiny papers that they put, not tiny, I mean, they're one finding, because they publish them in conferences and then they go on to the next thing. And the movement and the speed that this is happening at is absolutely extraordinary. You can't really keep up. So that is a problem, because ecologists aren't like that, like collect data for 4 years and then do some analysis. So I think there is a clash of cultures that we need to kind of try and bridge. But I've also seen people being really passionate about this area that are computer scientists and want to actually do something. So I know it's a really complicated question. I don't think I've got a good answer, but maybe. I don't know.
Yeah,
Oh, sorry.
While I understand that the last step saying decision is about having AI to predict several possible outcomes following different scenarios, while that's going to have a politician or leader to make the final decision. But this thing always happen because at the end, because AI will tell you which one is the best scenario anyway, and the politician may always go with the best scenario. So it would likely end up as AI is making that final decision. Do you think this is going to be really the point when AI rule our world?
Oh gosh, I hope not. I do think I'll be replaced soon, though, to be honest. I mean, just to come back to your point about politicians don't make rational decisions. You can present them with all the data and all the scenarios you like, but there are some politics going on, and there's some favors being done, or there's some lobbying being done, and so they don't often make the evidence-based decision. But I think maybe this is the optimist in me. If you can present stories which, if you do this happens, but you've got multiple dimensions to the scenario, so you can see the unintended consequences of this action, at least those decisions are more transparent about what you're actually saying when you say no to that restoration project or whatever. So I think these will help us create narratives which people can choose. Evidence-based narratives. How to influence the actual politician, I think that's a really complicated question. Will AI take over? Probably. Am I unhappy about that? Well, I could retire and go and sit in a cottage in Stroud.
Couple back there and move forward.
Thank you. Great talk. Do you think that technologies like the AMI system and bioacoustics will ever be able to capture true abundance of insects or bats and birds?
I think it depends what region you're talking about. If it's the tropics, I think we're miles away from there in the global south because we just don't have the libraries. So I think a lot of work needs to go on there. For some of them, I think possibly. I worked on this kind of random encounter model, which kind of models abundance rather than, gets it from the data rather than having to rely on marked individuals, which you have you don't have in acoustics. And whether we could test that out, that would be good. I don't know. I think that I think the statistical ecologists are kind of waking up to the fact that they don't have these observations are different now. They're kind of modeled probabilities of an observation. And actually that changes the stats, which you might want to do for occupancy and abundance. So I think there's a rich area there that we need to be talking to the statistical ecologists more to create new methods to account for the kind of false positive, false negatives in the data. So that's a really cool area. So I'm not saying no, but I think we do need to do some work on that.
Thanks, Kate. Great talk. You mentioned briefly recent advances in molecular methods and eDNA, etc. How does that fit into the whole large-scale sensing and AI advances? Are we going to have networks of DNA sensors that will give us amazing wide-scale molecular detection?
I think we actually have them already, but we haven't actually deployed them appropriately. So one of my new hires at the new centre that I have in East London, Joanne Littlefair, she's got a project looking at eDNA in the air. And she uses already air monitoring networks across the world that collect the sample and then they put it in the freezer. So actually we already have a global monitoring system for biodiversity if we use air DNA. So I think, yes, I think we will have these. Whether we'll have edge ones, I don't know, but maybe that's the next thing. I went to one of my colleagues at Microsoft, who earns an extraordinary amount of money, is developing this edge processing system for mosquitoes. So he has a whole box where there's a laser. Of course, there's a laser. There's a laser, and the wing beats of the mosquito break the laser, and then it there's an AI that tells them what species it is. And he's generating more data by having these kind of incubator boxes. He gives them to different countries, different labs, and then they generate the data from there. They breed these mosquitoes and give them to. Anyway, he's got the eDNA in there as well. So he takes those samples and then does the analysis, but it's not automatic yet. But maybe that would be the start of those. But they're kind of prototypey, so they're not like going to be roll-outable. But that's what they're working on at the moment, which is really exciting. So that's just to kind of monitor disease outbreaks and thinking about mosquitoes as vectors and where they're increasing.
Thanks for the amazing talk. I'm a bit curious because I'm working on like environmental benefits to human, and I'm kind of like being inspired by you hinted on. There's a lot to be done, like linked to the human perspective and when a human participation. But one of the thoughts I'm being curious about, maybe it's naive of me, but I think when the recording devices in the city parks, they recorded all the sound. and then potentially they're gonna record it, car drive past, and then people talk. And then is that can be using the AI to model in a way become a human acoustics?
Some ethical things. Yeah, no, I guess you could actually. You could think about sentiment analysis of the recordings, but gosh, that's a bit of an ethical nightmare. Like of recording people's chats, you know, that's really hard. I mean, we got around it by the edge processing. That's the only way we were allowed to put them up by the council, because we're processing, we're not storing anything, we're processing it on the sensor. So it said bat, not bat, or pipistrelle, not pipistrelle, whatever. So we weren't getting any, you know, there were humans just chatting going, what's that, you know? But we weren't getting that, and we wouldn't have been allowed to put them up if we had. So I think there's a huge debate now in conservation about the ethical aspects of putting camera traps out and sensors, and also if you're putting them out in a different country and you've gone there to do a survey and you come back with all that, whose data is that? Is that your data or is it their data? It's probably their data. But that's not covered by Nagoya or anything. That's not covered by any agreement. There's lots of stuff on genetics, but nothing on observations. So that's really interesting. I don't know, I probably over to you though on that one.
You would need ethics for that. If you wanted to publish the data.
Few online ones, so I'll relay some of those. First one is from Dustin Benton. How far are you from feeling confident that you could pay landowners in function of their species abundance, and what would be needed to change to make that possible?
How, say that again, how
Pay landowners in function of their species abundance, or I suppose, you know, some sort of automated detection system, and what would be needed to make that possible?
I don't think we're very far off, actually. I think I'm working with Alex now on a new audio moth that can actually embed some of our models on them, and they're like 50 quid. So, you know, or 7 quid, some of them, you know, so I think you could relay them across the site and have a platform to pull all the data together. Things about how I think the questions now are, where do you put them to get a robust estimate? And what are you actually trying to achieve with this huge data project? So I don't think we're far off. Maybe a year, maybe 2.
Well. Okay, great. Another question here. There have been concerns raised around AI's environmental footprint, and you probably need to get one like this. How do you think we can strike a balance of using it for nature recovery and its environmental footprint?
It's a really great question. Something I really worry about too. Maybe stopping using the large language models to ask, you know, who's won the football. I mean, that would be a good start. But you know, thinking about some of these projects I described are not possible without a model to help me, and you know, I couldn't do them. And if the scale that we need to be at to recover nature, we cannot do it by some of the methods we've been using, because you know it hasn't worked. So yeah, I don't know the answer. Maybe we could restrict its use or make it more expensive. But you know, can I just remind you that you already use machine learning and AI already? You use regressions on your computer, you know, like that. It's just a kind of rebadging of this. You know, I think maybe they're talking about large language models. Maybe that's what you're talking about. But you already use machine learning every day if you're a statistical scientist. I mean,
okay, and then one more. This one's, I'm a designer specializing in interventions, change in complex adaptive systems. Applying design expertise would avoid technology-led approaches and deliver the fit-for-purpose scenario you finished your talk on. Would you consider working with designers?
of course, yes, that would be awesome. Talk to me, email me.
That's Claire Boardman, if you. Okay, I think we have time for a few more questions from the audience, if anybody else has any. Okay.
Thanks.
Thank you so much for your talk. It has been one of the most interesting ones for me so far. It made me think a lot about my work and what I used to do. And we wanted to study jaguar populations using this device that was attached to the camera trap to identify individuals. But what I'm trying to say is that the main constraint or limitation of this wasn't AI itself. It was more the satellite that we were using to receive the images.
Wow.
And I also thought about recording the audio, and we couldn't process that because of we didn't have the computers that we needed to process that. So I want to ask you, what do you think are the main limitations of I realize these are outside of AI. Like, to me, the main limitations to AI are outside of the
actual thing.
the
It's
actual
about
thing.
processing.
And what are the
Yeah.
main challenges, and like, what do you think is the future of this in conservation?
That's a really great question. I think the technology is becoming better in terms of the connections to the satellite. There's more satellites, which is its own problem, but there's more satellites, so there's more connection. These devices are much smaller, much cheaper. There's a £7 one I saw last week, which can process all of this stuff on it and send it up to the cloud, wherever you want. Amazing. You know, so I think these are getting cheaper and cheaper and cheaper. I mean, that's also got its own problems. But so I think technology will help you with those things. And I also think that open source tools will also help you. So Google Colabs is really great. So Colabs it's completely free up to a point. You can get access to their GPUs and their CPUs if you need them. And that's completely free. I mean, obviously, if you're going to upload terabytes of data, it might not be, but you might have to pay. But that's kind of an easy access to some of these really powerful tools. And it's in a Jupyter notebook, so you can put some of the Python code that you've been working on up there. It's really easy to use. So I just use that. I'm not from Google, obviously, but I'm just trying to say there are new open source projects which will help you get to where you want to go. And WildMe is maybe a really good place to have a look at for Jaguar ID as well. That'd be really cool. Not as cool as tigers, obviously.
Thank you.
Next one's from Emily Lewis Brown. I wonder whether it's possible and useful to use these data in AI to reconstruct images and sounds of the nature we have lost, and what the reconstruction process from here might look like for scenario planning and decision making, and to capture imagination, buy-in, and energy for nature recovery. Maybe is this underway?
Brilliant idea. Yeah, I think it's really. I think you know we're storytellers. We have been since we were evolved. So I think stories are really, really powerful. I used to teach science communication to that one in the audience, but like it's really, really powerful. So how do we tell stories better? You know, we need to get better at storytelling. So I think AI recreating environment would be really amazing. I worked with Ella on a project where we came up with scenarios of in the UK of habitats, you know, say peat bog or whatever, and we looked at a degradation gradient of that peat bog, and we gave it different indicator species which were present in that area, and then you could see them declining over time. So you had like these different scenarios and then we gave them, not us, but what the people we were working with, gave them as choices in a choice experiment to see how much they would pay to restore nature. And so that was a really powerful narrative about, you know, how much would you actually pay to see this goldcrest or curlew or whatever. And it gave kind of energy to and evidence to DEFRA to, you know, have confidence in some of the policies that they were rolling out. So I think narrative storytelling is incredibly powerful.
Great. One more here. Thinking about the UK, can you use what you've learned from working with Yo Valley to develop plans to engage with many more farmers across entire landscapes? And might AI help with connecting up nature better than we seem to have achieved so far? And are you aware that there's clusters of farmer clusters in the UK who could be part of that?
Yeah, I think Yo Valley is unusual because they're very progressive. And I think because they're a dairy farm, they need to be. But they're really keen to get involved. And I think there's a lot of appetite at Yo to work with scientists, work with academics to deliver and understand interventions. And someone like Yo also has like hundreds of other farms that they have in their farm cluster. So they have got a really influential, they're acting as an influential broker within that whole region in Oxfordshire and Somerset and Gloucestershire. So I think working with farmers is something that we should have done like 100 years ago, not now, but okay, it's better late than never, but we should be having these conferences together with them and workshops with them much more than we have. So I went to a biodiversity leaders workshop a couple of weeks ago that was just about farming. It was farmers who were really interested in biodiversity, and okay, they're on the edge of the distribution of what farmers are interested in, but they were really interested in working with us. So I think, I think they've had a bad experience maybe with the NGOs in the past, and working with different organizations who are blaming them, but I think we need to bring them in and work with them more.
Great. That sounds like a
Can't
good
remember what I
note a good note to end on. So we have drinks around the corner. If anyone wants to linger and have a more informal conversation, you're welcome to join us there. Otherwise, thank you very much.